Hello. In this video, we discuss an amazing result which essentially classifies all finite abelian groups. But let me start by recalling that if G and H are two groups, then by component-wise multiplication, we can make G cross H into a group. Namely, we define the operation to be to send G1, H1 dot G2, H2 to G1 times G2, H1 times H2, where I'm using multiplication in the first group, in group G, for the first component, and I'm using the binary operation of the second group, H, for the second component. So I'm essentially doing component-wise multiplication. Because multiplication is done for each component separately, the question of whether or not G1 and G2 commute, whether or not this pair commutes with the other pair, boils down to the question of whether or not G1 commutes with G2 and H1 commutes with H2. And that means the Cartesian product of two groups, G cross H, is an abelian group precisely when both G and H are abelian groups. Okay, so now starting with cyclic groups, using Cartesian product, we can construct many finite abelian groups. Remember, cyclic groups are abelian. So I start with cyclic groups Z sub n sub 1, Z sub n sub 2, and so on. And then I take Cartesian product of these groups. We end up getting a finite abelian group. Not all finite abelian groups of this type are different from isomorphism point of view. If you remember by Chinese remainder theorem, we know that if m and n are coprime, then Cartesian product of Z sub m and Z sub n is isomorphic to the cyclic group of order mn. So not all the groups of this type are distinct from isomorphism point of view. But nevertheless, we are getting a lot of finite abelian groups. In fact, there is this amazing result which says that every finite abelian group is of this form. For every finite abelian group, in fact, we can find unique integers with the following properties: that n1 divides the next one, n2 divides the next one, and so on. And our given finite abelian group is isomorphic to Z sub n sub 1, Cartesian product with Z sub n sub 2, and so on. So this additional condition gives us a way to get rid of phenomena like this. And now there is a unique set of integers n sub i's that this abelian group is going to be isomorphic to Z sub n sub 1 Cartesian dot Z sub n sub k and n sub i's, each one divides the next one. We are going to call this form, this type of abelian groups, we are going to call them the standard form of the abelian group A. So I give you an abelian group and I ask you, can you find the standard form of A? Then that means you have to give me this sequence of integers, each one dividing the next one, and showing that this abelian group that I'm giving you is isomorphic to Cartesian product of Z sub n sub i's. This is a very nice result, and we are not going to prove the result in this course, but rather we are going to see how we can find standard forms of given abelian groups, standard form of given abelian groups. Okay, let's see some examples. Notice that I've mentioned this example using Chinese remainder theorem that if n and m are co-prime, then z sub n cross z sub m is a cyclic group, and therefore it is in fact isomorphic to z sub n. Now the next example uh, says that this is in fact if and only if a statement, meaning z sub n cross z sub n is not cyclic if m and n are not co-prime. Let's see why this is the case. This shows that this example, you cannot write it as a single z sub n, z sub k for some k, because it's not cyclic. So you need at least two cyclic groups in order to write this. But what is the standard form of this abelian group? We are not going to discuss in this example. Here we just want to show that it's not cyclic. Okay, let's see why this is the case. Because GCD of m and n is not 1, let's call it d, and that d is going to be a positive non-positive integer more than 1. And notice that mn divided by d then is both a multiple of n, because I can write this as m over d, and that's an integer because d divides m, times n, or I can write it as m times n over d, and again n over d is an integer because d divides n. That means that mn over d is an integer which is both a multiple of n and a multiple of m. It's a common multiple of n and n. In fact, one can show that this is the least common multiple of m and n, but for this example, we don't need this statement. We only need to use the fact that mn over d is a common multiple of m and n. So it's a common multiple of m and n. Now let's see how this can help us to show that z sub n cross z sub m is not cyclic. What we will do is we will show that every element of this group, order of every element of this group divides mn over d, and therefore it cannot be mn. And so this group, which has order mn, has no element of order mn. That means it cannot be a cyclic group. Okay, so let's go through the details of the argument. For every a and b integers, if I look at this pair and multiply it by mn over d, remember here we are in the additive setting, so instead of using exponential notation, we have to use multiplication notation. So I'm going to multiply this pair of integers, pair of elements, by mn over d. Then the first component, I'm going to use that mn over d is an integer multiple of n, and deduce that because n times this is 0, this first component is 0. Similarly, this time I'm going to think about mn over d as an integer multiple of m, and because m times a number that's residue class mod m is 0, we deduce that the second component is also 0. So we end up getting the pair of zeros as we multiply this pair by mn over d. And that means that the order of this element should divide mn over d. So the order of every element inside this group is at most mn over d, and that is strictly less than mn. Remember, the assumption is that d is not 1. D is at least 2. So mn over d is strictly less than mn. And therefore, this cannot be a cyclic group because it has no element of order the same as its cardinality. That implies that it is not cyclic. Okay. Now, in order to see how we can find a standard form of groups of this type, we are going to actually work out some examples. So let's start with the following example. Find the standard form of z sub 12 cross z sub 10. Notice that neither of these integers divide the other one, so this itself is not the standard form of this abelian group. Now, how do we do it? The idea is to follow the following steps. First, split it into powers of primes and then regroup them in a way that you can use, you end up getting the standard form. So that's a very rough idea. But let's start breaking these terms, each one of them, into powers of primes. What does that mean? By Chinese remainder theorem, we do know that z sub 12 is isomorphic to z sub 4 cross z sub 3 because 4 and 3 are coprime. So this is what I'm doing. I'm writing 12 as product of powers of distinct primes, and then these distinct powers of primes, the power of these distinct primes, they are coprime to each other. Therefore, I can use the Chinese remainder theorem and write the cyclic group as Cartesian product of these cyclic groups whose orders are coprime to each other. In fact, the orders of powers of distinct primes. Similarly, z sub 10 is isomorphic to z sub 2 cross z sub 5. Now the point is that I'm going to look at Cartesian product of these two. I'm going to reorder the terms and gather all the powers of 2 close to each other, then powers of 3 close to each other, then powers of 5. So I'm going to regroup these terms in terms of the primes that are involved. So the prime factors that divide this length of, the size of these cyclic groups. So z sub 12 cross z sub 10 is isomorphic to, first I'm going to write down those factors that are powers of 2. That means z sub 2 cross z sub 4. Then I'm going to write down those factors that are powers of 3. I have only one here, so I write it over here. And finally, I'm going to write down those factors that are powers of 5, and I have only one over here, so I write it over there. So now I want to regroup them again and again use Chinese remainder theorem. Okay, now how do we do that? We are going to first ask ourselves how many factors do we have here that are powers of 2? How many factors do I have that are powers of 3? How many factors do I have that are power of 5? And order them and make a building out of it. So for instance, here I have 2 factors that are powers of 2. So that's the maximum. So I put it in the base and I write 2, 4. And then the next one, so 3 and 5, both of them are have only one factor. So it doesn't matter what order we pick. So let's pick the smaller one, put it on top of 2. So then that means we start these blocks from the right hand side. So I put this 3 over here on top of 4, and then 5 on top of 3. So these are all the blocks that are responsible, that appear in this Cartesian product. Now I want to group them together, and I notice that if I go over each one of these columns, I end up getting powers of distinct primes, and therefore they are co-primed each other, and therefore I can group them together using Chinese remainder theorem. So what do I mean by that? So if I look at z sub 5, Cartesian product with z sub 3, Cartesian product with z sub 4, now these 4, 3, and 5, they are co-prime. So by the Chinese remainder theorem, this Cartesian product, only these 3 terms, is isomorphic to z sub product of 4, 3, and 5. So I put them together, and now I have z sub 2 separately, and I write it over here. So these Cartesian products is isomorphic to Cartesian product of these two cyclic groups. And now notice that Z sub 2, this 2 divides 60. And therefore, this is the standard form of this abelian group, because it is written as product of cyclic groups and the indices, each one divides the next one. So the algorithm again is that first we break them apart into powers of primes using Chinese remainder theorem, and then regroup them in terms of powers of primes, and then ask ourselves what is the maximum number of factors that we have corresponding to different primes, and start building them up, stack them on top of each other, and then go through the columns. So when I go through the columns, I get exactly the cyclic groups that appear in the standard form. So let's see one more example of this time, at least one more example. Actually, we'll see a couple of examples of this time. So find the standard form of this abelian group, Z sub 6, Cartesian product Z sub 15, Cartesian product Z sub 45. We follow our steps, factoring two primes and using the Chinese remainder theorem. So we have Z sub 6 is isomorphic to Z sub 2 cross Z sub 3. Z sub 15 is isomorphic to Z sub 3 cross Z sub 5. Z sub 45 is isomorphic to Z sub 9 cross Z sub 5. Now I want to regroup them in terms of prime factors. So powers of 2, I have 1 over here, and that's it. So that's the only factor that's power of 2. Powers of 3, I have 1, Z sub 3, Z sub 3, and Z sub 9. So there are 3 of them. Powers of 5, Z sub 5 and Z sub 5. So there are 2 of them. Now I want to make a building out of it. So there are 3 powers of 3. So that would be our largest block. So I put it in the bottom. Next, I have 2 blocks of 5. I put it on top of the blocks of 3, starting from right. So I get this. And finally, I have 1 block of 2, and I put it on top of those. So I get this building. Now, after creating this building, we look at each column and multiply them. And essentially, I'm again using the Chinese remainder theorem. So the abelian group that we are interested in is isomorphic to, now at this stage, I'm just reordering the terms. The first column gives me Z sub 3. The next one gives me Z sub 5 cross Z sub 3. The third one gives me Z sub 2 cross Z sub 5 cross Z sub 9. Now, using Chinese remainder theorem, the first one I don't touch, but the second one is Z sub 15, and the last one is Z sub 90. And notice that 3 divides 15, and 15 divides 90. And so it is the standard form of this abelian group. So we are done with this example now. Let's see another one. Make sure that we understand the process. We want to find a standard form of this abelian group, Z sub 20 cross Z sub 50 cross Z sub 30. Okay, so again, we start by factoring two primes. Z sub 20 is isomorphic to Z sub 4 cross Z sub 5. Z sub 50 is isomorphic to Z sub 2 cross Z sub 25. Z sub 30 is isomorphic to Z sub 2 cross Z sub 3 cross Z sub 5. Now again, I'm going to look at, I'm going to regroup them in terms of powers of primes. So I ask myself, which one of these blocks are powers of 2? I have 1 over here, Z sub 4, Z sub 2, and Z sub 2. How about powers of 3? I have Z sub 3, only 1 block of 3. How about powers of 5? Z sub 5, z sub 25, and z sub 5. So there are three blocks for powers of 5. Now we want to construct this building. So this is the regrouping that I was talking about. 3 factors for powers of 2, 1 for power of 3, and 3 for powers of 5. Now we are going to construct the building. First, the max, as we can see, is 3. So let's put 2, 2, 4 in the bottom. Then we put 5, 5, 25 on top of that. And finally, we put 3 on top of those. And then we go through the columns. So the first column is z5 cross z2. The next one is the same. The last one is z sub 3 cross z sub 25 cross z sub 4. Again, by Chinese remainder theorem, we get that the first one is z sub 10, the next one is z sub 10, and the last one is z sub 300. And again, notice that 10 divides 10, and 10 divides 300. So this is the standard form of this abelian group. Now, next we see how we can use the first isomorphism theorem to find the standard form of an abelian group, which is given as a factor group, as a quotient group. This task is not easy in general. So we deal with easy examples in order to illustrate how this can work out. This can be worked out. So we want to find the standard form of the abelian group that's given by this quotient. We look at z cross c and then mod it out by the subgroup that's generated by 2, 0 and 0, 5. So again, in general, in order to answer this type of questions, I give you Cartesian product of bunch of z's, and then I'm modding out by some subgroup that's generated by certain vectors. In order to answer these type of questions, to find the standard form of these type of abelian groups, one needs to use Smith form of certain integral matrices. And we are not going to discuss Smith form in this course. Here we are going to illustrate some basic examples and the ideas behind Smith form a bit. Okay, so let's do this example. Let's consider the following group homomorphism. We look at the homomorphism first. It might seem a bit magical, why did we consider it, and so on. But as we go through the argument, hopefully by the end of the solution, you get an idea that why this particular group homomorphism is suitable for this particular example. But let me mention this before we get to the argument. The main point of this example is that we have 2, 0, 0 is the second component here, and 0, 5, 0 is in the first component. The point is that we are working with these vectors that are multiples of the standard vectors E1 and E2, and that's why this example is rather easy. So here we are using 2 times E1 and 5 times E2, and that is why we can actually understand this quotient group rather easily. Okay, now let's look at the solution. So the group homomorphism sends z cross z to z sub 2 cross z sub 5. And what is f? I send the pair a comma b to a mod 2 and b mod 5, to the residue class of a mod 2 and the residue class of b mod 5. It is actually easy to check that it is a group homomorphism because each one of the components separately is a group homomorphism, and therefore when I put them together and multiplication or addition in this case is component wise, we can deduce that f is a group homomorphism. The other thing that we can point out is that every element in this Cartesian product, the first component is of this form, and the second component is of this form, and therefore F is surjective. So F is a surjective group homomorphism. I want to use the first isomorphism theorem in order to get some understanding about the quotient of Z cross Z. The first isomorphism theorem says that domain modeled by the kernel is isomorphic to the image. So in this example, that means Z cross Z modeled by the kernel of F, the quotient factor group of Z cross Z by kernel of F is isomorphic to image of F. We have already discussed what image of F is. Image of F is the entire codomain, is Z sub 2 cross Z sub 5. But what is its kernel? So that's why we are going to study kernel of F. Now, A comma B belongs to the kernel of F precisely when the residue class of A mod 2 is the residue class of 0 mod 2, and the residue class of B mod 5 is the residue class of 0 mod 5. And notice, in general, residue class of A mod n is the residue class of n 0 mod n if and only if n divides A. So in this example, A should be a multiple of 2 and B has to be a multiple of 5. That means the pair A comma B belongs to the kernel of F precisely when A comma B can be written as an integer linear combination of the vectors 2 comma 0 and 0 comma 5. Now you see why we considered this function F, this group homomorphism F. Because it was 2 comma 0 and 0 comma 5, it was easy to write down a group homomorphism whose kernel is the subgroup that's generated by 2 comma 0 and 0 comma 5. So that is essentially our goal. We wanted to find a group homomorphism whose kernel is the subgroup generated by the given vectors that we had. So this argument that we have over here implies that kernel of F consists of all the vectors that are integer linear combinations of 2 comma 0 and 0 comma 5. In particular, 2 comma 0 and 0 comma 5 are in the kernel of F. And so the subgroup generated by these two vectors is a subset of kernel of F. The next claim we show equality. We show that kernel of F is the subgroup generated by 2 comma 0 and 0 comma 5. So again, let me repeat that 2 comma 0 is an integer linear combination of 2 comma 0 and 0 comma 5, and the same is true for 0 comma 5, because that's 0 times the first vector plus 1 times 0 comma 5, and therefore both of them are in kernel of F. Now, this is the smallest subgroup that contains these two vectors, and these two vectors are inside kernel of F. Therefore, the subgroup generated by them is a subset of kernel of F. Now I want to show the other way around. Notice that every element of kernel of F is an integer linear combination of these two vectors. Now, if I give you a group like this that contains both 2 comma 0 and 0 comma 5, then it's going to contain all the multiples of 2 comma 0, all the integer multiples of 2 comma 0, and all the integer multiples of 0 comma 5 and their summation. So this means that these elements are definitely in the group generated by the vectors 2 comma 0 and 0 comma 5. So again, because this is a group that is closed under addition and subtraction, we deduce that closed under addition and subtraction, we deduce that for every integer r and s, for every pair of integers r and s, this integer linear combination of the vectors belongs to the subgroup generated by 2 comma 0 and 0, 5. And so kernel of f, because every element of kernel is of this form, we get that kernel of f is a subset of the subgroup generated by these two vectors. This result, together with this one, the claim implies that kernel is indeed the subgroup generated by 2, 0 and 0, 5. Now I am in a good place to use the first isomorphism theorem. By the first isomorphism theorem, therefore, we have that z cross z over kernel of f is isomorphic to the image of f. Remember, f is surjective, and kernel of f is generated by the vectors 2, 0 and 0, 5. So we end up getting this isomorphism, that this factor group that we are interested in is isomorphic to z sub 2 cross z sub 5. Now notice that 2 and 5 are coprime, therefore by the Chinese remainder theorem, this Cartesian product is isomorphic to the cyclic group Z sub 10. And that's the standard form of this abelian group. So kind of because of this special example, we got lucky. And because it was 2, 0, 0, 5 integer multiples of the standard basis, we got lucky and we could easily find a standard form of this quotient. And if you look at it closely, you see that the same argument implies that if I start with positive integers m and n, then z cross z over the subgroup generated by m, 0 and 0, n is isomorphic to the Cartesian product of the cyclic groups z sub m and z sub n. Now, what if I change these? Then what happens? Can I have non-zero components on this part? So in general, the question would be much harder to answer. But the next result can help us to address some of the subtleties. So suppose I give you two pair of integers, a sub 1, b sub 1, and a sub 2, b sub 2. So they are pair of integers. And then I look at, I also assume that the matrix that I get out of putting these a1, b1, and a2, b2 on the columns of this 2 by 2 matrix, this matrix has determinant either +1 or -1. That's the assumption. And remember, determinant of 2 by 2 matrix is a1 times b2 minus a2 times b1. So that's the assumption. And this difference is supposed to be either +1 or -1. If this is the case, then the following function is an automorphism of z cross z. So the function is from z cross z to itself. I feed it a pair of integers m, n, and it asks me to look at the integer linear combination of these vectors with coefficients m and n. So I'm looking at m times the first vector plus n times the next one. So that is f. And claim is that this f is an automorphism of this abelian group z cross z. Okay, the first thing that we do is to, similar to linear algebra, we are going to view this function as a matrix multiplication. We are going to write elements of z cross z not as pair of elements, but rather as 2 by 1 column vectors. So I'm thinking about z cross z as 2 by 1 column vectors. And then what does the function f do? When I feed it this column vector mn, what it does is giving me the column vector, if you look at this, m times a1 plus n times a2, that's the first component, and m times b1 plus n times b2 is the next component. So the function f sends this column vector mn to this column vector m times a1 plus n times a2, m times b1 plus n times b2. And that's nothing but multiplying this 2 by 2 matrix by the given column vector mn. So the function f is simply multiplying by this fixed matrix. I give it a vector, it multiplies that vector by this fixed 2 by 2 matrix from left. Now let's see why it's an automorphism. Let's start with checking why it's a group homomorphism. But now that's easy because we know multiplication distributes. So for every two vectors in Z cross C, as I multiply this 2 by 2 matrix by V plus W, I can distribute and I can multiply this matrix first by V and then by W. And that means that F sends V plus W to this product, it sends V to this product, and it sends W to this product. And all together we see that it sends V plus W to what it does to V plus to what it does to W. Therefore, it's a group homomorphism. So F is a group homomorphism. Why is it invertible? Similar to linear algebra, we turn our attention to the inverse of the matrix. Again, let's recall that inverse of a 2 by 2 matrix is easy to compute. If I give you a 2 by 2 matrix, x11, x12, x21, x22, its inverse is, okay, we take its determinant and compute 1 over determinant. And then we flip the order of diagonal entries, and the other ones we multiply by -1. So a negative x12, negative x21, and this is inverse of the matrix x11, x12, x21, x22. Now, here is the crucial fact that helps us to show that the function f is invertible. The assumption that determinant of the initial matrix that they started with is either +1 or -1 implies that this is still an integer. That's the key point here. This is an integer. Of course, these are still integers. That's the assumption. And altogether with these two assumptions, we deduce that inverse of this integer matrix is still have entries in Z. So inverse of this integer matrix itself is an integer matrix. And therefore it sends Z cross Z to itself. And if I write it in the particular case of this question, the example dilemma that we are discussing, we deduce that the function that sends V to the multiplication of inverse of this matrix by V still sends Z cross Z to Z cross Z because this inverse itself has integer entries, and therefore I'm sending an integer vector to an integer vector. That's the crucial thing. Again, this assumption helps us to deduce that this is definitely an integer, and therefore the whole thing has integer components. Now, knowing that this function sends Z cross Z to Z cross Z, again, one can see that it is a group homomorphism. This is in fact the inverse of the function f, because the function f multiplies by this matrix without inverse, and this function multiplies by the inverse of that. So if I apply one after another, the inverse cancels out the matrix that they started with. We end up getting the vector v, and that means the composite of these two functions is the identity function, and therefore it's inverse of f. And that shows that f is invertible. F is a group homomorphism, and it is invertible, therefore it is an isomorphism. It sends Z cross Z to itself, and so it is an automorphism. Okay, so these type of functions are automorphisms of Z cross C, and in fact one can show that these are all automorphisms. I mean, this is the entire set of automorphisms of Z cross C. That one I'm not discussing in this video, but it's an easy argument, and I encourage you to think about it, that the entire set of automorphisms of Z cross C can be described as we did in this particular lemma. The converse of this statement is also true. Okay, now let's see how this lemma can help us to understand a standard form of some quotient groups, some factor groups. So let's say I want to find the standard form of the factor group Z cross C over the subgroup that's generated by 3 times 2, 1 and 5 times 3, 2. Here, I'm not working with standard vectors. 2, 1 is not 2, 0, 1, 0, and this is not 0, 1. So I cannot use the idea that we had before and simply send this to Z sub what? We don't know what. If it was 6, 0, and this was 0, 10, we could have sent it to Z sub 6 and Z sub 10. But in this case, it's not clear what the target should be. But let's look at the vectors that we are given, 2, 1 and 3, 2. These vectors, if I put them in a column of a matrix, I end up getting a matrix whose determinant is 1. 4 minus 3 is 1. So determinant of this 2 by 2 matrix is 1. And that means, by the previous lemma, the function from Z cross Z to Z cross C, which sends the pair m comma n to m times the first column plus n times the second column, is an automorphism of Z cross Z. See, now we are in the realm of this. I'm considering some integer multiple of this and some integer multiple of this. And we are saying these integer linear combinations, in fact, if I consider all of them, I get back the entire Z cross Z. The F is an automorphism of Z cross Z. Okay, so what? Now let's consider the following function. So we start with Z cross Z. I send it to Z cross Z using F. So that way the standard vectors go to these vectors 2, 1 and 3, 2. Again, let me go back in this page. Let's see where F sends 1, 0. So 1, 0 is sent to, I have to put 1 here and 0 here. So this disappears. I end up getting only the first term. That's 2, 1. And where does it send 0, 1? 0, 1 is sent to, this time I have to plug in 0 for m and 1 for n, and therefore the first term disappears and only the second vector resists. So this F sends the standard vector 1, 0 to 2, 2, 1, and 0, 1 is sent to 3, 2. And that's kind of what we wanted. If this guy was 1, 0 and this guy was 0, 1, we could have used our earlier technique and use the map to Z sub 3 cross Z sub 5 and get an isomorphism between this factor group and Z sub 3 cross Z sub 5. So that's what we are doing essentially. This F is trying to help us to change the basis, so to speak, in order to have a nice denominator in this factor group. So that's the goal of this method. So we have this automorphism F, and then I have this natural quotient map from Z cross Z to the quotient of Z cross Z by this group that's generated by 3 times 2, 1 and 5 times 3, 2. Let's call the composite of these two functions F bar. Notice that both F and P are surjective group homomorphisms, and therefore their composite is also a surjective group homomorphism. So F bar is a surjective group homomorphism. I want to use the first isomorphism theorem for F bar. We have already discussed what image of F bar is. Next, I'm going to understand what kernel of F bar is. So a pair of integers belong to the kernel of F bar precisely when P of F of this pair is 0 in the factor group. But 0 in the factor group means that this element should be in the kernel of P. So f of r comma s is in the kernel of P. And that means r comma s is in the inverse of f applied to kernel of P, but kernel of P is this group. So this means the pair r comma s should belong to f inverse applied to the subgroup generated by these two vectors. F bar itself is a group automorphism, so I can apply this to each one of the generators. So the group generated by these two vectors, this group, is the same. After I apply F inverse, I can apply it multiplication by 3 flips and switches with the order of F inverse, addition, permute with the order of F inverse. F inverse is a group homomorphism. So as I apply F inverse to this one, it's like applying F inverse to each one of these terms and then looking at the smallest subgroup that contains those two. So I get that this is the subgroup that's generated by 3 times F inverse of 2 comma 0 and 5 times F inverse of 3 comma 2. Now I am in a good position because we know that F inverse of 2 comma 1 is 1 comma 0. Again, recall that 1 comma 0 is mapped to 2 comma 1. So inverse of F applied to 2 comma 1 is 1 comma 0. And inverse of F applied to 3 comma 2 is 0 comma 1. So this is 1 comma 0 and this one is 0 comma 1. Therefore, this group is the group generated by 3 times this and 5 times this. And 1 r comma s should belong to this group. Altogether, we deduce that kernel of F bar is this group. Now we are in a good position because by the first isomorphism theorem, I know Z cross Z is the factor group of Z cross Z by the kernel of F bar is isomorphic to its image. Remember, F bar is surjective, so I get that image of F bar is the entire factor group of Z cross Z. Remember, F bar goes to this group. So I get the entire thing as an image of F bar, so that's this side. On the other side, I have Z cross Z, and kernel of F bar is the subgroup generated by these two vectors. Now, all of a sudden, I've changed these crazy vectors to standard vectors. Now I can use the previous example and deduce that this factor group is isomorphic to Z sub 3 cross Z sub 5. And now I can use the Chinese remainder theorem and find the standard form of this factor group and deduce that this is isomorphic to this one, and this one is isomorphic to Z sub 3 cross Z sub 5. In order to do this step, it is similar to the previous example. Let me quickly say that you consider this map. You argue that it is surjective and its kernel is given by these two. From these two, we can deduce that it is isomorphic to this using the first isomorphism theorem. Now, by the Chinese remainder theorem, this is a cyclic group of order 15, and that completes solution of this example. So in this video, we discussed the standard form of a finite abelian group. We did not prove why we do have this uniqueness and existence, but we discussed how we can use Chinese remainder theorem in order to find the standard form of certain finite abelian groups. And we also discussed some ideas behind the Smith form and the connection between the Smith form and finding a standard form of a finite abelian group that's given as quotient of Z cross Z or Z cross Z cross Z modeled by certain subgroups. In the next video, we will discuss how group actions can help us to understand finite p groups, finite p subgroups of a finite group. So when I say p group, I simply, in this, for the purpose of this course, we mean a group that has order p to the n, where p is a prime number.